Most welcome for today's lesson. Today we are going to look at carbon and its compounds like I had promised you last time. We are going to be handling this topic because it is a little bit wide in a series of videos. So this is the first video on carbon and its compounds. Before we begin, I would request you to continue subscribing on my channel. It's called Smart Science, and keep watching these videos such that at the end of the day we can come up with a better understanding of the science. So today, like I had promised you previously, we are discussing carbon and its compounds. And during the discussion, we are going to break it into carbon itself. Then we are also to look at compounds of carbon. So under here, I'm beginning with carbon as the first part of the topic we are looking at today. We all know that carbon is an element. It's an element in group 4. In group 4 of the periodic table. This element of carbon has an atomic number. It has an atomic number of 6. And because of this atomic number of 6, its electronic configuration is 2 to 4. Because of that, it gives carbon a stable valence of 4. So it has a stable valence of 4. Its mass number is 12. So basically, this gives us the introduction of carbon and whatever we are to look at under carbon as an element. This element exists in different compounds. So we look at its occurrence. Where do we expect to find carbon? In its pure form, pure carbon exists in diamond. Pure carbon exists in diamond naturally. And then impure carbon exists in an element known as graphite. However, we have other components or other compounds where we can find carbon. So carbon also exists. Carbon also exists in organic compounds. It also exists in organic compounds. It can exist in substances like coal. It can exist in carbonates, in combined states, etc. There are very many compounds where we can get carbon from. So as we discuss carbon, look at where it exits. And these two are going to give us what we call the allotropes of carbon. These allotropes are going to be crystalline as part of the compounds where carbon can be obtained from. As we proceed on the introduction of carbon, this takes us to allotropes of carbon. How can we talk about the allotropes? Next in line, allotropes of carbon. Carbon shows us allotropes, but before we discuss those different allotropes, we need to understand what the following terms mean. Allotrope. If I say allotrope, what do I mean? This is the existence of an element. Existence of an element in more than one form. In more than one form, without change of its physical state. Without change of its physical state. If it is a solid, all the forms will be solids at room temperature. So those different structural forms are the ones we are calling allotropes. These ones are the different structural forms. The different structural forms in which an element exists without change of state. Without change of state. So when it comes to allotropes of carbon, there are those that are crystalline and there are those that are not crystalline. So carbon has three main allotropes. And these ones include diamond, graphite, then amorphous carbon. These two are crystalline. These are crystalline forms, and amorphous carbon is non-crystalline. So if you meet a question which requests you to give us the crystalline allotropes of carbon, we are to name diamond and then graphite. However, before I proceed, there are other elements that show us allotropes. So I would like us to summarize other elements which have allotropes. Among them, include 1, oxygen. This oxygen is going to show us 2 allotropes, dihydrogen oxygen, the one we breathe in, and 2 trioxygen, commonly known as ozone. This one is O3. It forms the ozone layer. Sulfur is another element which can show us allotropes. Among the allotropes of sulfur, we have amorphous sulfur, we have monoclinic sulfur, and we have rhombic sulfur. Three is phosphorus, which shows us white. Sometimes it is called yellow phosphorus. And then it shows us red phosphorus, among others. So when we come up with the word allotrope or allotropes, just to know that we look at the different forms through which these elements exist without change of their physical state. It is only the appearance or the color that will change, but the physical state remains the same. To take you through these allotropes, we are to begin with diamond, and as an example of an allotrope of carbon, diamond, we are going to begin by looking at its physical properties. I'm sure you've watched very many movies dealing with diamond stones, and one of the things you've identified is that it has a crystalline structure. So has a tetrahedrocrystalline structure. Number 2, you've identified that these kind of stones are colorless. And because of being colorless, these stones are transparent. They are transparent with a shiny appearance. The next characteristic or physical property of this diamond, it's a very hard substance. Actually, it is the hardest we know on Earth. So, very hard substance, in brackets, hardest on Earth. It's the most hard substance we know on Earth. 4, non-conductor, i.e. can't conduct electricity. We are to see the reasons as to why it cannot conduct electricity through its structure. All the electrons are used in bonding, such that no free electron is left to conduct electricity. That's why diamond is a non or a poor conductor. Next comes on its density. So has a very high density. The density is very, very high, to approximately 3.5 grams per cubic centimeter. That is the projected density of diamond. When we proceed, we have to look at the structure of diamond. Structure of diamond. We have to ensure that at the back of our minds, we already know that carbon is a non-metal. It is not under groups of elements we call metals. So expect any kind of bonding between carbon atoms to be covalent. Okay? So when we come up with the structure of carbon, I mean the structure of diamond, it has a tetrahedrocrystalline structure in which each carbon atom is covalently bonded. Each carbon atom is covalently bonded to 4 other carbon atoms. That is number 1. So this structure extends in a 3-dimension. It extends in a 3-dimension in which or where bonds interlock. And when they interlock, making diamond a very hardy substance. So within the structure of diamond, the bonds are going to interlock, and that explains why diamond is a very hardy substance, as we've said here in the physical properties. When we continue with the structure of diamond, you're going to see to it that all the valence electrons, of carbon are used up in bonding. Thus, localized. Hence, diamond can't conduct electricity. So the reason as to why diamond cannot conduct electricity is because the electrons, the valence electrons, cannot move. They are fixed, they are localized. That's why there is no conduction of electricity, because of the localized electrons of diamond. So when we look at the drawing, of the structure, take C as the symbol of carbon. We've agreed that each carbon is bonded to 3 other carbon atoms in a tetrahedral structure. And this carbon should also be bonded to 3 others in a tetrahedral structure. Likewise, this carbon has to bond with 3 others. Even this one has to bond with 3 others. That's why in some books you're going to find us trying to simplify the drawing concerning the structure of carbon in the simplest way possible. However, the points I would like us to identify are these points where the bonds interlock, which makes carbon a very hard substance. Number 2, where each carbon atom is bonded to 3 to 4 other carbon atoms. Think you're seeing that 1, 2, 3, 4, such that all the valence electrons are used up in that bonding. When it comes to uses of diamond, the uses are derived from the properties of diamond. Because diamond is transparent and shiny, it's going to be used to make jewelry. Used to make jewelry. Due to its shiny appearance. Two, diamond is going to be very vital in industries for making drilling and cutting machines of substances. So used in industries to make drilling and cutting machines. Among others. So those are some of the uses of diamond we can phrase here. Number 2 is graphite. This is another allotrope of carbon. And on graphite, we have to begin with the physical properties. What are some of the physical properties of graphite as an allotrope of carbon? Number 1, it's black. It has color and opaque. Doesn't allow light to pass through it. Has a relatively lower density of about 2.3 grams per cubic centimeter. It's a soft substance. It is a soft substance, unlike diamond, which is hard. Graphite conducts electricity. Due to free mobile electrons. When it comes to the structure of graphite, we are going to see to it that graphite has a hexagonal ring structure. And in this structure, each carbon atom is bonded, and this bonding should be specific. Each carbon atom is covalently bonded to 3 other carbon atoms. We are going to see to it that the structure of graphite extends in a 2-dimensional structure. So the structure extends in a 2-dimensional structure. So instead of being a 3-dimension like diamond, graphite is a 2-dimensional structure. These hexagonal rings we are talking about, the hexagonal rings form layers that are joined by weak van der Waals forces of attraction, allowing the layers to slide over each other, making graphite a soft and slippery substance. So within the physical properties, this property of being soft is due to the weak van der Waals forces of attraction that allow the graphite layers to slide over each other when describing the structure of graphite. As we continue with the structure of graphite, you're going to see to it that not all the valence electrons of carbon are going to be used up in the bonding. So the 4th valence electron in carbon is not bonded. Thus, free and mobile. These two words can be replaced by delocalized. Hence, graphite conducts electricity. When we try to represent this on a drawing or a diagram, take it to be carbon forming hexagonal rings with other carbon atoms. To pull out the structure very well, I would like to represent my carbon with a dot. So where you see a dot is a carbon atom. So the carbon atoms combine with each other, forming hexagonal rings. These hexagonal rings are connected in such a way that each carbon atom is bonded to 3 other carbon atoms. So if I form another layer, if you see to it that we form another hexagonal ring layer, you are to see to it that these ones are connected by the weak van der Waals forces of attraction. They are to be connected by the weak van der Waals forces of attraction. And these forces come due to so these are the van der Waals forces of attraction. Van der Waals forces of attraction. What I'm representing as a dot is a carbon atom. This is a hexagonal ring. Hexagonal ring. This is a covalent bond. Okay. These are layers. Those are layers as shown. So that is the structure of graphite. This is the first layer and this is the second layer. So when it comes to the structure of the two crystalline forms of carbon, that is how we can basically describe the structure. And lastly, on graphite, I would love to end graphite by looking at its uses. Where do we apply graphite? How can we use graphite? Uses of graphite. Number one, are used to make pencil leads. When you're writing in pencil, just know you're using graphite. Two, used as an electrode. In electrolysis, which is also a topic that we are going to handle here, but I imagine all my learners out there have ever seen a battery. So those electrodes, those terminals on a battery where you connect the wires onto, should be made out of graphite. Used to make electric conductors. Used to make electric conductors. Those are some of the uses of graphite we can discuss. As we continue, we look at the third allotrope of carbon, which we called amorphous carbon. Amorphous carbon. What are the physical properties? Just like we've seen for the previous allotropes of carbon. So amorphous carbon is black. That is the color. And most commonly, the color of carbon is going to be black. Among all the allotropes of carbon, it has the lowest density. And this density, we are not going to quote it because quoting is not necessary. but just know among the three main allotropes of carbon, it has the lowest density. Shapeless, so it is non-crystalline. That's why we call it shapeless. It forms no shape. That's why we call it amorphous. And lastly, the poor conductor of electricity. Poor conductor of electricity. So amorphous carbon has a variety of examples depending on the substance being given off. You're not going to find carbon named amorphous carbon there, but we're going to see various examples of amorphous carbon, various examples of carbon without a particular shape. Okay, so among those examples include examples of amorphous carbon, examples of amorphous carbon. Number one, we have wood charcoal. Wood charcoal. This one is used as a source of fuel, obtained by burning. It is obtained by burning wood in limited air, and it is used as a source of fuel used for cooking, the charcoal we normally use. Number two is animal charcoal. If you want this, it is obtained by roasting animal bones in limited air. And this one used as a bleaching agent to remove the brown color of sugar. Remove the brown color in sugar such that we get white crystals of sugar. Number three is coke. This one formed by heating coal in absence of air. Formed by heating coal in absence of air. Among its uses, we are going to see it as a used as a reducing agent during extraction of iron. When we are extracting iron, coke is used to reduce the ore. Number four is lamp black. This one is mainly formed by burning of oils. Formed by burning oils in limited air. Formed by burning oils in limited air. Lamp black is useful. The oils, we mean kerosene. Kerosene is paraffin, petrol, those things. If you burn them in absence of air, you're going to get lamp black. And it is used in making shoe polish. So I would love to see people trying out how we make shoe polish using lamp black. So as we are summarizing this particular part, before we look at the properties of carbon and before we look at the other parts of carbon, I want us to respond to the following questions. Can you be in a position to state the differences between the two crystalline forms of carbon? Are you in position to describe the structure of graphite? And are we in a position to name any other three elements that show allotrope apart from carbon? So try to put yourself into classroom environment and try to respond to those questions, which will give us a better understanding on the allotropes of carbon. And question number three is what I'm going to respond to. Describe an experiment to show that graphite, diamond, and amorphous carbon are allotropes of carbon. Is there any evidence we can give to show that those three are really allotropes of carbon? And if they are, what should tell us that graphite, diamond, and amorphous carbon are all allotropes of carbon? So my response is going to be on question number three. That is solution for question number three. I would love you to handle question 1 and 2. So as I'm summing up today's lesson, because we are to look at properties, chemical properties of carbon in another video, and we shall pick it up from there to look at the compounds of carbon. So solution to this question is same mass of graphite, diamond, and amorphous carbon is burnt separately in excess oxygen. When you do that, same volume of carbon dioxide is evolved. And if that is so, you conclude by saying all the three substances contain the same element of carbon, and that shows us that graphite, diamond, and amorphous carbon are all allotropes of carbon. So in our next video log, we are going to look at the chemical properties, the reactions of carbon, and thereafter we look at the compounds of carbon, where we have to discuss carbon dioxide and carbon monoxide and the organic compounds. It will take us through the organic chemistry. So today we are pausing from here. I would end by requesting you to continue subscribing to my channel, because we are going to be receiving these episodes quite more often, and we continue our learning process until when we come up with a collective understanding of chemistry. I wish you a nice stay. Thank you very much. Remember, my YouTube name is Smart Science. So search, subscribe, and watch my content. Thank you very much.